Hello, and welcome to the Science to Sleep channel. I'm really glad you're here. Maybe today was long and tiring, or maybe you just enjoy falling asleep while thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, you're in the right place tonight. There's nothing you need to do now. Just let your body relax, allow your breathing to slow, and let your thoughts drift gently. Tonight we're exploring the universe itself. Not just a single star or galaxy, but the vast, expanding whole. We'll move slowly from one calm fact to another, learning about black holes, ancient light, dark matter, and distant galaxies. Some ideas may quietly surprise you. Others may stay with you like a soft thought as sleep approaches. And if these peaceful explorations help you rest, you're welcome to like and subscribe. It helps others find their way here too. Now, whenever you're ready, let's begin. The universe might be older than we think. Most modern estimates place its age at about 13.8 billion years. This number comes from measurements of the cosmic microwave background and the rate at which space is expanding. But not every method agrees perfectly. Some observations of very old stars and distant galaxies suggest ages that seem difficult to fit into this timeline. Others question whether the expansion rate has always been constant or whether dark energy changes over time. These questions remain unresolved. Most astronomers still accept the 13.8 billion year estimate, but the uncertainty lingers. Could the universe be older? Did we overlook something essential? It's possible that what we call the beginning was only one chapter in a much longer, stranger story. There are thousands of rogue planets drifting through space without stars. Not every planet belongs to a solar system. Some worlds travel alone, unbound to any star, moving quietly through the galaxy. These rogue planets may have formed around stars and later been ejected by gravitational chaos. Others may have formed entirely on their own, like failed stars. They are cold, dark, and nearly invisible, revealed only when they pass in front of distant stars, or glow faintly in infrared light. Astronomers estimate there could be billions of them in the Milky Way, possibly more than the number of stars themselves. Each one is a silent world drifting through darkness, spinning alone between the stars. The universe may recycle itself through endless cycles. The standard cosmological model describes a universe that began with the Big Bang and continues expanding, possibly forever. But some theories imagine a different rhythm. In these models, the universe expands, slows, collapses, and then begins again. Instead of ending, it resets. Each cycle could erase most traces of the previous one, while still preserving faint echoes. These ideas are speculative, but fascinating. They suggest a universe without a true beginning or end, only a slow, cosmic breathing, expanding and contracting across unimaginable stretches of time. The oldest light we can observe comes from about 380,000 years after the Big Bang. Before that moment, the universe was a hot, dense fog where light scattered endlessly. As space expanded and cooled, atoms finally formed and the fog cleared. Light was suddenly free to travel. That ancient glow still surrounds us today as the cosmic microwave background. It's the oldest direct signal we can observe, not from stars or galaxies, but from the universe itself becoming transparent for the first time. Those photons have been traveling for more than 13 billion years, stretched into faint microwaves by the expansion of space. A quiet, ever-present echo of the universe's first clarity. Some stars may have planets made almost entirely of diamond. In certain systems, chemistry plays out very differently than it does here. If a planet forms with far more carbon than oxygen, intense pressure can turn much of it into crystalline carbon. Astronomers have identified at least one such candidate orbiting a pulsar, the dense remnant of a dead star. Based on its mass and density, this world may be a giant diamond. It wouldn't sparkle, and it would be unbearably hot. But deep inside, vast diamond lattices could stretch for thousands of kilometers. These planets are rare, but they remind us how creatively the universe builds its worlds. The universe may have no edge, only curvature. It's natural to imagine a boundary to space, some distant edge we could eventually reach. But space doesn't appear to work that way. According to general relativity, space can curve without needing an edge. Current evidence suggests the universe is either infinite or so large and gently curved that it loops back on itself. In that case, traveling straight forever could eventually bring you back to where you started, not by hitting a wall, but by following curved space. Much like walking around Earth, never finding an edge, only a continuous surface. The Sun may once have had a twin. Many stars form in pairs, and some astronomers believe our Sun was no exception. If it had a sibling, that star would have drifted away long ago, pulled apart by the slow gravitational tides of the Milky Way. It may still exist somewhere, orbiting the galaxy on a distant path. Some speculative ideas even link this lost twin, sometimes called nemesis, to extinction events on Earth, though no evidence supports this. Still, the thought remains that our quiet sun may once have shared its birth with another, now lost among the stars. A single raindrop of neutron star material would outweigh Mount Everest. Neutron stars are the collapsed cores of massive stars, left behind after supernova explosions. They're only about 20 kilometers wide, yet contain more mass than the Sun. Inside them, matter is crushed so tightly that atoms collapse, forcing electrons and protons into neutrons. A teaspoon of this material would weigh billions of tons. These objects are small, dark, dense, and often spinning rapidly, holding matter in one of its most extreme forms. Light from one galaxy can reach us from multiple directions. In regions with immense gravity, space itself bends. This curvature can redirect light, a phenomenon known as gravitational lensing. As a result, we can sometimes see multiple images of the same distant galaxy. These appear as arcs, rings, or repeated smudges in deep space images. In rare cases, even the same supernova has been observed more than once, its light arriving along different curved paths. Light can wander, take the long way, and still arrive. The first stars may have burned 1,000,000 times brighter than the Sun. These earliest stars formed from pure hydrogen and helium, with no heavier elements at all. They were massive, hot, and short-lived, sometimes hundreds of times heavier than our Sun. They burned quickly and exploded after only a few million years. None survive today, but they forged the first heavy elements and shaped the early universe. Their light is gone, but their influence remains. Dark matter passes through your body as you sleep. Our galaxy is surrounded by a vast halo of dark matter. As Earth moves through it, countless dark matter particles pass through your body every second. They don't interact with your atoms and leave no trace, but they're there. Without dark matter, galaxies wouldn't form the way they do. We still don't know what it's made of, but it quietly shapes everything. Some galaxies glow without stars. Astronomers have found faint galaxies filled with gas and dark matter, but almost no stars. Some may have lost their stars. Others may never have formed many at all. They drift quietly through space, challenging what we thought we knew about galaxy formation. The universe has a cold spot that shouldn't exist. In the cosmic microwave background, there's a vast region colder than expected. It spans hundreds of millions of light years and doesn't fit neatly into existing models. Some think it's a massive cosmic void. Others wonder if it hints at something stranger. For now, it remains an unanswered whisper in the background of the universe. The moon is slowly moving away from Earth. Each year it drifts about 3.5 centimeters farther. This slow separation has been happening for billions of years, caused by tidal interactions. It's subtle, but relentless. One day, Earth and the moon may become tidally locked. For now, the moon simply continues its quiet retreat. Some binary stars exchange matter like a slow dance. In close binary systems, stars can pass material back and forth, sometimes gently, sometimes violently. These interactions can create strange, powerful objects and dramatic events. Even stars, it seems, can share, change, and sometimes merge. The vacuum of space is not truly empty. Even in the deepest void, quantum fluctuations constantly create and destroy particles. Space hums quietly with activity. This restless energy may even drive the universe's expansion. So even in perfect darkness, nothing is truly still. Time doesn't move the same way everywhere in the universe, even if it feels that way to us. We tend to imagine time as steady and fair, ticking forward at the same pace for everyone, no matter where they are. But in reality, time is deeply tied to gravity, motion, and the shape of space-time itself. Where gravity grows stronger near a black hole or inside a dense cluster of galaxies, time slows down compared to regions where gravity is weaker. This isn't just an idea on paper. It's been tested, measured, and confirmed with satellites and atomic clocks. Some cosmologists take this even further and wonder if time might vary across the universe on the largest scales. Could different regions experience time slightly differently because of how the universe expanded in its earliest moments? It's still speculative, but the question itself is unsettling. In a universe ruled by relativity, time may not be universal at all. It may stretch, slow, or bend, quietly shaped by the space it moves through. When we picture the Milky Way, we usually imagine a bright spiral of stars glowing against the dark. Dust, gas, and light arranged in familiar sweeping arms. But that glowing disk is only part of the story. Surrounding it is something far larger and mostly invisible, the galactic halo. This enormous region extends far beyond the visible edge of the galaxy, reaching many times the width of the disk itself. It contains ancient star clusters, wandering stars, and vast amounts of dark matter. Gravity holds it together, while billions of years of mergers and collisions have shaped it. We can't see the halo directly, but we know it's there from the way stars move and light bends. The Milky Way turns out to be less of a whole object and more like a bright core, wrapped inside something much larger and quieter. The universe is about 13.8 billion years old, but light doesn't move instantly. It travels through expanding space, stretched and delayed along the way. That's why when we look far enough, we're not seeing things as they are now, but as they were long ago. Using the James Webb Space Telescope, astronomers have detected light from a galaxy that existed just 200 million years after the Big Bang. On a cosmic clock, that's barely a moment. That light has been traveling toward us for more than 13.5 billion years. The galaxy itself is small and faint, still forming, still figuring itself out. But it carries clues about how the first structures emerged. Observing it feels like peeking through a narrow crack in time, into a universe that was only just learning how to shine. When astronomers map galaxies across immense distances, a strange pattern appears. Galaxies don't scatter randomly. They line up along long filaments, leaving huge empty voids in between. This structure spans billions of light years and is known as the cosmic web. What's eerie is how familiar it looks. Zoomed out, it resembles a neural network, like the wiring inside a human brain. Dense clusters look like nodes. Filaments look like connections. The universe isn't thinking, of course, but the resemblance is hard to ignore. Two systems shaped by completely different laws ending up with a similar structure. It's one of those quiet moments where scale stops mattering. Space itself doesn't carry sound, but stars still vibrate. Inside a star, pressure waves ripple through hot gases, bouncing back and forth like seismic waves through a planet. These vibrations cause the star to subtly pulse. Scientists detect them by watching tiny changes in brightness or surface motion. This field is called asteroseismology, the study of starquakes. Each star has its own internal rhythm, shaped by its size, age, and structure. By listening to these vibrations, scientists can figure out what's happening deep inside a star. It's a strange kind of listening. No sound, no air, just silent waves revealing hidden interiors across light years. Galaxies don't form all at once. They grow, collide, merge, and reshape themselves over time. Because of this, some stars inside a galaxy can actually be older than the galaxy's current structure. These ancient stars may have formed in smaller systems long before they were absorbed into something larger. Today, they often live far from the center or inside globular clusters. Some are more than 13 billion years old, nearly as old as the universe itself. Their chemistry reflects a time when heavy elements were rare and the cosmos was still simple. They're stellar fossils, quietly shining with light that began before much of the universe took shape. Dark matter is supposed to be the glue that holds galaxies together. It explains why stars move the way they do and why galaxies cluster across space. But recently, astronomers have found galaxies that don't seem to follow this rule. Galaxies that behave as if dark matter isn't there at all. Their stars move as though only visible matter exists. This was unexpected and uncomfortable. Some think dark matter was stripped away during violent encounters. Others suspect our understanding is still incomplete. Either way, these galaxies remind us that the universe doesn't care what we expect. Some rules may bend or break entirely. Deep inside the sun, pressure waves bounce around continuously, setting the whole star into subtle vibration. These waves are far too slow and deep for human hearing, but sensitive instruments can detect them. This field, called helioseismology, lets scientists map the sun's interior, its density, rotation, and hidden flows of hot plasma. In this sense, the sun is always ringing. Like a vast instrument we're only beginning to understand. By listening carefully, we learn not just about our own star, but about stars everywhere. The universe's largest structures aren't built from light, but from darkness. Dark matter forms immense filaments stretching across space, and galaxies tend to form along them like beads on a string. We can't see these filaments directly, but we know they're there from how galaxies cluster and how light bends as it passes through. Between them lie enormous voids, regions with almost nothing inside. Dark matter acts like a hidden framework, quietly shaping where galaxies grow and how they move. Even now, we don't know what it's made of. We only know it's there, holding everything together without ever showing itself. Nothing can move faster than light through space, but space itself plays by different rules. In the early universe, space expanded so quickly that regions were pulled apart faster than light could travel between them. This wasn't motion through space, but the stretching of space itself. Even today, distant galaxies recede not because they're speeding away, but because the space between us keeps growing. If they're far enough away, they'll eventually slip beyond what we can ever observe again. The universe doesn't rush. It simply expands, calmly and endlessly. The planets don't just orbit the sun in flat circles. The sun itself is moving, orbiting the Milky Way at incredible speed. As it travels, the planets follow, creating a slow spiral through space. Everything moves, nothing is fixed. Even as you sleep, you're tracing a gentle helix through the galaxy, wrapped in motion you'll never feel. Even empty space has a temperature. Far from stars and galaxies, the universe sits at about 2.7 Kelvin, just above absolute zero. This warmth comes from the cosmic microwave background, the cooled afterglow of the Big Bang. It fills all of space, everywhere, quietly reminding us of the universe's origin. In the far future, it will cool even more, but never quite reach zero. Even emptiness remembers. At the smallest scales, reality flickers. Tiny fluctuations appear and vanish due to quantum uncertainty. During the universe's earliest moments, inflation stretched these microscopic ripples into cosmic structures. Galaxies, filaments, voids, all may trace back to random quantum tremors. Everything we see today may have grown from brief instability at the edge of nothing. Some dying stars don't explode, instead they pulse. Their outer layers expand and contract in slow rhythmic cycles, changing brightness over time. These variable stars beat like long cosmic heartbeats. Some take days, others take years. Their rhythms help us measure distances and track the scale of the universe. Even at the end, stars can keep time. Our solar system drifts inside a vast bubble of hot gas called the local bubble, carved out by ancient supernova. It stretches hundreds of light years across. We can't feel it, but it surrounds us, a quiet reminder of violent events long past. Beyond the great attractor lies an enormous void called the dipole repeller. One region pulls galaxies in, the other pushes them away through emptiness. Together, they shape our motion through space. Presence and absence both matter. Trillions of neutrinos pass through your body every second. They come from the sun, distant stars, and the early universe. They barely interact with anything. They pass through planets, through you, unnoticed. Motion everywhere. Silence everywhere. And sometimes the most massive stars don't even explode. They collapse directly into black holes. No flash, no farewell. Just a quiet ending, hidden from view. Some stars are so massive that when their fuel finally runs out, there's no dramatic explosion to mark the end. Their cores collapse inward so completely, so suddenly, that gravity wins instantly and even the outer layers fall straight in. No supernova, no final blaze, just absence. This is called a direct collapse. One moment the star exists, the next it's gone, replaced by a black hole, silent, invisible, unimaginably dense. Astronomers have actually seen stars that seem to simply vanish, as if someone turned off the light. It's a reminder that not every ending in the universe announces itself. Some endings don't shout, they slip quietly into the dark. We often imagine galaxies as lonely islands drifting far apart, but many of them live together. In small groups they interact, pull on each other, and sometimes even orbit one another. The Milky Way itself has dozens of satellite galaxies. The large and small Magellanic Clouds are the most familiar examples. These companions move around our galaxy much like moons orbit a planet, following long, slow, elliptical paths. As they dance, larger galaxies can steal stars from their smaller partners, stretching them into faint streams and tidal tails that span millions of light years. Over time, a smaller galaxy may be completely absorbed. These encounters take billions of years, slow, graceful, and almost gentle on cosmic scales. Even galaxies, it turns out, don't always travel alone. Some of the brightest explosions in the universe may come from collapsing magnetic stars. There's a rare event called a magnetar hypernova, and it may be one of the most powerful explosions nature can produce. A magnetar is a neutron star with a magnetic field so strong it defies intuition, trillions of times stronger than Earth's. If a massive star collapses into a magnetar and releases its energy rapidly, the result can be an outburst far more intense than a typical supernova. These events are thought to power some long-duration gamma-ray bursts, brief flashes that can outshine entire galaxies. The explosion lasts seconds, but its light can cross billions of light years. All that power coming from a tiny, dense object wrapped in magnetic fury, collapsing inward under its own gravity. When we talk about the edge of the universe, we're really talking about the edge of what we can see. The observable universe extends about 46 billion light years in every direction. That isn't a wall or a boundary. It's simply the farthest distance light has had time to reach us since the Big Bang, while space itself keeps expanding. Beyond that, the universe likely goes on. We just don't have access to it. And because expansion is accelerating, some regions are moving away faster than light, meaning their light will never reach us, no matter how long we wait. The observable universe is a bubble of awareness. Not the whole thing, just the part we're allowed to witness. At the center of many galaxies sits a supermassive black hole, and sometimes those black holes announce themselves in unexpected ways. As matter falls inward, not all of it disappears. Some gets caught in powerful magnetic fields and is launched outward in narrow jets of plasma, moving at nearly the speed of light. These jets can extend far beyond the galaxy itself, stretching millions of light years into space. We see them glowing in radio wavelengths, forming enormous lobes that trace their reach. These systems, called radio galaxies, host some of the largest structures in the universe. It's a strange contrast. The strongest outflows come from places where light itself struggles to escape. Not every star in the Milky Way follows the same path. Most orbit the galaxy in the same direction, carried along by its rotation. But there are exceptions. At least one known star, HD 4357-439, moves at the opposite direction on a retrograde orbit. It cuts against the flow like it doesn't belong. One explanation is that it came from another galaxy that merged with the Milky Way long ago, bringing its own orbital history with it. Another is that it was flung into this path by a powerful gravitational encounter. Either way, it's a reminder that even in a system as orderly as a galaxy, there are rebels drifting through. The center of the Milky Way contains molecules that, on Earth, we associate with very familiar smells. Astronomers studying a cloud near the galactic core found ethyl format, a compound linked to raspberries and rum. Space doesn't smell, of course. There's no air to carry scent. But the chemistry is real. Interstellar clouds contain alcohols, sugars, and complex organic molecules. Not life, but the kind of chemistry life might one day build from. Even in the harshest regions of space, complexity quietly assembles itself. The Andromeda Galaxy is on a collision course with the Milky Way, and in a way, it's already begun. Andromeda sits about 2.5 million light-years away, but it's moving toward us. In roughly 4 billion years, the two galaxies will merge. Their outer halos, vast clouds of hot gas and dark matter, already overlap. The eventual encounter won't be a crash. Stars are too far apart to collide. Instead, it will be a long, graceful blending, reshaping both galaxies into one larger elliptical system, sometimes called Milkomeda. A meeting already written into the future. All around you, right now, there's a faint glow filling space. The cosmic microwave background is the afterglow of the Big Bang, light released when the universe was about 380,000 years old. Before that, the cosmos was opaque and hot. Once atoms formed, light could finally travel freely. That light has been moving ever since, stretched by expansion into microwaves. We detect it today as a nearly uniform background in every direction. It's the oldest light we can observe, a quiet echo from the universe's earliest moments. Not all supernovae shine brightly. Some stars die in near silence. In what are called failed supernovae, a massive star's core collapses into a black hole, but the outer layers never explode outward. Instead, they fall inward and vanish. Astronomers have watched stars simply disappear without warning. There's enormous violence in these events, but almost all of it is hidden behind gravity. Another reminder that the universe doesn't always announce its most dramatic moments. Some galaxies are barely visible at all. They contain few stars, but plenty of gas and dark matter. These faint systems are difficult to detect and may represent galaxies that never fully formed or lost their ability to create stars early on. They don't glow, they don't spiral, they simply exist, held together by gravity. Quiet members of the cosmic population, when black holes orbit each other, they slowly spiral inward, losing energy through gravitational waves. These ripples in space-time travel outward at the speed of light. When the black holes finally merge, enormous energy is released, not as light, but as distortion itself. In 2015, we detected these waves for the first time, confirming Einstein's prediction. Since then, we've heard dozens more. Each one is a silent collision, shaking the fabric of the universe. Smaller stars die slowly. Stars like our sun expand into red giants, shed their outer layers, and leave behind white dwarfs. These dense remnants don't burn fuel. They simply cool very slowly over billions of years. The universe isn't old enough for any to have cooled completely. Every white dwarf ever formed is still glowing faintly somewhere. Near a black hole, time itself slows down. This is gravitational time dilation, a real effect predicted by general relativity and measured in weaker forms near Earth. Close to a black hole, minutes could pass for you while years pass elsewhere. Black holes don't just trap light, they stretch time. The space between galaxies is colder than any place on Earth. With almost no matter to hold heat, temperatures drop to just a few degrees above absolute zero. These vast voids are the coldest, quietest regions we know. Over time, the universe has become more transparent. Once opaque and glowing, it now allows light to travel freely across billions of light years. Darkness didn't come from emptiness, but from clarity. In 2019, we captured the shadow of a black hole. The image from the Event Horizon telescope showed the dark silhouette of the black hole at the center of galaxy M87, outlined by glowing gas. It wasn't science fiction. It was light, finally bent into proof. And on a clear night, you can see another galaxy with your own eyes. The Andromeda Galaxy appears as a faint smudge in the sky. Its light began traveling toward you millions of years before humans existed. And yet, here it is, still arriving. Andromeda holds around 1 trillion stars, more than twice as many as the Milky Way, and it's slowly drifting closer to us. It sounds unreal, but on a clear night you can look up and see an entire galaxy with nothing but your eyes. No telescope, no filter, just the sky, a quiet moment, and the soft glow of something ancient and unimaginably vast moving through the dark. One small instrument once caught the faintest whisper of a black hole collision. In 2015, a sensitive detector called LIGO noticed something extraordinary, a tiny ripple in space-time arriving from over 1 billion light-years away. It came from 2 black holes spiraling into each other, shaking the universe itself. The effect was unbelievably subtle. By the time it reached Earth, space stretched and squeezed by less than the width of a proton. Yet with enough precision we could hear it. LIGO and its partner observatories work like cosmic ears, tuned to the deepest murmurs of existence. This moment confirmed a century-old prediction by Einstein, showing that even the quietest corners of space can carry echoes of violent events. A single chirp from invisible giants detected on a small blue planet sitting quietly in the dark. Some parts of the universe are already slipping away from us forever. Space is expanding, and that expansion keeps accelerating. Certain galaxies are being pushed away so fast that their light will never reach us, no matter how long we wait. The distance between us grows quicker than light can cross it. They've crossed a cosmic point of no return, fading beyond the event horizon of the observable universe. Over immense spans of time, more of the cosmos will disappear from view, not because it vanishes, but because its light can no longer arrive. The universe isn't just growing larger, it's slowly letting go. Not all black holes may come from dying stars. Most form when massive stars collapse, but some may be far older. These hypothetical objects, called primordial black holes, could have formed in the earliest moments after the Big Bang, before stars or galaxies existed at all. Tiny density fluctuations in the newborn universe may have collapsed into ultra-compact knots of matter. Some could be microscopic, others might have grown over time. We haven't found one yet, but if they exist, they could explain dark matter, help seed galaxies, or reveal secrets about the universe's first seconds. They would be older than stars, older than galaxies, silent fossils from the dawn of time itself. Entangled particles might connect distant corners of the cosmos. Quantum entanglement is one of physics' strangest ideas. When 2 particles become entangled, their properties stay linked regardless of distance. Change one and the other responds instantly, even across vast separations. This doesn't allow faster-than-light communication, but it hints that reality is deeply interconnected at a fundamental level. Some scientists think entanglement may even play a role in the structure of space-time. Particles created in the early universe could still be entangled today, stretched across cosmic expansion. If so, invisible threads may still connect far-flung regions, quiet quantum echoes lingering between galaxies. Empty space isn't truly empty. Even in a perfect vacuum, with no atoms or radiation, energy still exists. Quantum physics tells us that space is filled with restless fluctuations. Particles briefly appear and vanish. Fields shift subtly, nothing ever fully still. This creates what's known as vacuum energy. On the largest scales, it may help explain dark energy, the force behind the universe's accelerating expansion. Unlike ordinary energy, vacuum energy doesn't thin out as space grows. It remains constant, pushing space to stretch faster over time. It's strange to think that nothingness itself might be driving the universe apart. Black holes aren't completely silent forever. Despite their darkness, quantum theory predicts that black holes emit an incredibly faint glow called Hawking radiation. Near the event horizon, particle pairs can form with one falling in and the other escaping. The escaping particle carries energy away, slowly draining the black hole. Over timescales far beyond comprehension, this process causes black holes to shrink and eventually evaporate. A black hole with the mass of the Sun would take far longer than trillions upon trillions of years to disappear. It's not a dramatic end, just a slow, quiet fading. Most matter in the universe isn't solid at all. While we're used to solids, liquids, and gases, the dominant state of matter in the cosmos is plasma. Plasma is an ionized gas where electrons and nuclei move freely. It fills stars, flows in solar winds, drifts through interstellar space, and stretches between galaxies. Plasma responds to magnetic fields, carries electric currents, and behaves unlike anything we commonly see on Earth. Here, it appears briefly in lightning or neon signs. Out there, it's everywhere, glowing and shaping the universe on massive scales. Gravitational waves move at the speed of light. When massive objects like black holes or neutron stars collide, they send ripples through space-time itself. These waves stretch and compress space as they pass, racing outward at the universe's ultimate speed limit. It took decades to build instruments sensitive enough to detect them, but now we can listen. Each wave carries details about distant catastrophes, mass, spin, distortion. They're silent to human ears, yet real and measurable. Tiny shivers in the deep structure of reality. Galaxies form a vast cosmic web. On the largest scales, matter in the universe isn't scattered randomly. Galaxies trace enormous filaments of dark matter and gas, forming a structure known as the cosmic web. Where filaments intersect, superclusters emerge. Between them lie vast voids, nearly empty regions of space. We can't see this web directly in a single image, but it appears through massive sky surveys. It resembles foam, branches, even neural networks, not chaotic, but woven. The James Webb Space Telescope sees galaxies that no longer exist. Because light takes time to travel, Webb observes the universe as it once was. Some galaxies in its images may have already merged, changed, or vanished entirely. Their light is still arriving, carrying ancient information across space. Telescopes don't show us the present, they show us history. Every deep image is a time capsule, filled with light from things long gone. Some galaxies shine with light older than Earth itself. When you see a galaxy billions of light years away, you're seeing it as it was before the Sun formed. That light traveled across expanding space, stretching and reddening until it finally reached us. The stars that created it may no longer exist. The glow remains, a reminder that the night sky is full of stories older than our world. Entire galaxies can hide behind dust. Thick clouds of interstellar dust can block visible light, concealing massive structures. These grains, made of carbon and silicates, drift through cold molecular clouds. Galaxies hidden behind them only reveal themselves in infrared, radio, or X-ray wavelengths. What looks like empty space can be full of unseen worlds, waiting for the right light to be noticed. Some galaxies create perfect rings of light. When gravity bends light just right, it forms an Einstein ring, a glowing circle caused by gravitational lensing. The mass of a foreground galaxy curves space-time, wrapping distant light into a loop. These rings are rare and stunning, formed by alignment rather than motion. They help astronomers measure mass, map dark matter, and study the early universe. Natural illusion shaped by gravity itself. the universe may have no edge at all. Observations suggest space could be infinite. We can only see a finite region, the observable universe, but beyond that, space may continue endlessly. No boundary, no center, just more. Most of it will always remain unreachable, a quiet vastness without conclusion. Cosmic rays constantly strike Earth. High-energy particles from the sun, distant stars, and violent cosmic events rain down on our planet every second. Most are deflected or absorbed, but some pass through you unnoticed. They're harmless reminders that space is active, filled with motion and energy. Each particle carries a story that began far away. There may be no meaningful before the Big Bang. In many models, time itself began with that event. Asking what came before may not make sense, like asking what's north of the North Pole. Some theories explore earlier states or cyclic universes, but in most cases the Big Bang wasn't an explosion in space. It was the beginning of space. Astronomers once mistook quasars for stars. Early on, quasars appeared as faint points of light. Their strange spectra puzzled scientists until it became clear they were distant galaxies with violently active cores. Powered by supermassive black holes, quasars can outshine entire galaxies. Their light traveled billions of years to reach us, masquerading as simple stars. Our local group is drifting toward something unseen. The Milky Way, Andromeda, and their companions move together toward a massive gravitational anomaly known as the Great Attractor. Beyond it lie regions hidden by the dense plane of our galaxy. We can measure the pull, even if we can't see the source. It's as if our entire neighborhood is sliding toward unseen giants in the dark. We are living in the universe's stellar springtime. Stars are forming, burning, and exploding all around us, but this era is temporary. In the far future, star formation will fade. What we see now is a brief, luminous season in cosmic history. For the first few 100 million years after the Big Bang, there were no stars at all. Everything existed in darkness. Then the first stars formed, quietly lighting their surroundings and setting cosmic evolution in motion. Since that moment, star formation rose, reached its peak, and has slowly declined. We now live in what could be called a cosmic spring, a time when stars are still being born, fewer than before, yet far more than will exist in the distant future. One day the final stars will form. After that, the universe will gradually grow dim, but for now there is still light, still beginnings, bright enough to wonder, gentle enough to rest. In the far future, stars will stop forming altogether. Star birth depends on cold gas, vast clouds of hydrogen and helium collapsing under gravity. Over time, that fuel becomes scarce. It gets locked inside stars, blown away by supernova, or heated beyond use. Billions of years from now, galaxies will run out of the raw material needed to create new stars. The ones that remain will grow old, burn out, and fade. First, the massive blue giants, then sun-like stars, and finally the red dwarfs, until even the slowest embers cool into darkness. The universe won't end suddenly. It will dim in stages, quietly and patiently. What remains will be black holes, white dwarfs, neutron stars, and a cosmos grown cold. Not tragic, just still. Most of the universe is invisible. When we look at the sky, stars, galaxies, glowing clouds, we're only seeing a small fraction of what's really there. Most matter doesn't shine. It doesn't emit or reflect light. This unseen substance is called dark matter. We haven't detected it directly, but its presence is clear through gravity. Galaxies rotate faster than they should. Light bends more than expected. Clusters stay bound with more force than visible matter allows. All signs point to a hidden mass, more than 5 times the amount of ordinary matter. Dark matter surrounds us, shaping the universe silently. We can't see it, but everything depends on it. Light from the first galaxies has been stretched by the expansion of space. As light travels, it doesn't simply move forward. Space itself expands beneath it, stretching the light along the way. Light that left the earliest galaxies billions of years ago has been pulled into longer wavelengths, shifting from visible into infrared. This effect is called redshift, and it's one of the main tools astronomers use to measure distance and age. The more stretched the light, the farther and older its source. Telescopes like James Webb can finally detect this ancient glow, softened by time and distance. What began as brilliant starlight now arrives as a quiet whisper, carried by the universe's slow breath. The universe might be a hologram. It sounds like science fiction, but some physicists take the idea seriously. According to the holographic principle, our three-dimensional universe could be a projection from a deeper two-dimensional reality. This idea comes from black hole physics, where information appears to be stored on a surface, not throughout the volume. Some theories suggest the universe itself might work the same way. What we experience as depth and space could emerge from encoded information on a distant boundary. It's not proven, and it won't change your daily life, but it hints that reality may be stranger and subtler than it looks. Space itself may not be smooth. To our eyes, space seems continuous and empty. But some theories of quantum gravity suggest it may be made of tiny discrete units, like pixels in an image. This smallest scale is called the Planck length, around 10 to the negative 35th meters. At that level, smooth space may break down into something granular, foamy, and fundamental. We don't yet have tools to test this directly. But if it's true, then everything happens not in a perfect void, but within a universe that has structure all the way down. Some stars spin faster than kitchen blenders. Certain stars rotate so quickly that they bulge at the equator, their surfaces smeared by speed. Neutron stars take this to an extreme. A special kind called millisecond pulsars can rotate hundreds of times per second. Imagine a city-sized sphere of nuclear matter spinning faster than a blender blade. These stars emit beams of radiation that sweep across space like cosmic lighthouses, ticking with incredible precision. Many steal matter from companion stars, spinning even faster. They are among the fastest rotators in existence, and also some of the most precise clocks, quietly keeping time in the dark. The universe may end in a long, quiet fade. Once scientists wondered if everything would collapse back inward. Now evidence suggests endless expansion. As galaxies drift apart and star formation slows, the sky will grow darker, stars will burn out, black holes will evaporate, matter itself may decay. This slow future is called heat death. Not an explosion, not a freeze, just a gradual thinning of energy and structure. Over immense time, the universe grows quiet, not ending in fire or ice, but in silence. Some galaxies breathe out superwinds. In galaxies with active black holes or intense star formation, powerful winds can erupt from the core, carrying gas, dust, and even young stars into intergalactic space. These superwinds can stretch tens of thousands of light years. Driven by radiation, magnetic fields, and exploding stars, they slowly strip galaxies of star-forming material. Over time, the galaxy grows quiet and red, but those winds also spread heavy elements, seeding future stars and planets elsewhere. In this way, galaxies inhale, ignite, and exhale back into the void. The far future will resemble a dark ocean. Trillions of years from now, galaxies will be so far apart that each appears alone. No new stars will form. Old ones will fade. Even white dwarfs will grow dark. What remains will be scattered remnants, black holes, and ancient particles drifting through emptiness. Over vast time, black holes will evaporate and matter itself may decay. Eventually, only motionless particles remain. This isn't a sudden ending. It's a deep, endless stillness, a cosmic ocean without waves. We might live inside a giant cosmic void. Between clusters of galaxies lie enormous empty regions called voids, spanning hundreds of millions of light years. Some scientists think we may be inside one of these underdense regions. If true, it could help explain certain measurements of cosmic expansion. Living in a void doesn't change daily life, but it means what feels like emptiness is part of a much larger structure, a quiet bubble drifting through a web of gravity we cannot see. Magnetars have magnetic fields trillions of times stronger than Earth's. A magnetar is a neutron star with a magnetic field so powerful it can distort atoms and erase data from across the galaxy. These fields decay over time, but while they last, magnetars release intense bursts of radiation. A single flare can be detected from across the Milky Way. Nothing on Earth compares. They are extreme, silent remnants wrapped in invisible force. The largest known structure is a giant quasar group. In 2013, astronomers discovered a massive structure spanning over 4 billion light-years, made of connected quasars. It challenges the idea that the universe should look smooth on the largest scales. Whether it's a true structure or a coincidence is still debated. Either way, it reminds us that the universe may be more complex and connected than we expect. Black holes twist space into funnels of time. Near a black hole, space bends inward and time slows. At the event horizon, time nearly stops from an outside view. Inside, all paths lead inward. Space and time trade roles. You cannot turn back. This isn't metaphor. It's geometry written by gravity. Some regions of the universe will never meet again. As expansion accelerates, some areas move apart faster than light can cross the space between them. No signal will ever arrive. Galaxies become isolated islands. Nothing breaks physics. Space itself expands, calmly separating everything forever. Gold is born in cosmic violence. It doesn't form inside ordinary stars. Instead, it's forged during neutron star collisions and rare supernovae. In those moments, matter is crushed into heavy elements. That gold spreads through space, becoming part of planets and people. Every piece of gold carries the memory of catastrophe. Space stretches light as it travels. Distant light is redshifted not because it slows, but because space grows beneath it. The universe stretches the signal. When we see distant galaxies, we see space breathing. There are sound waves frozen into the cosmos. In the early universe, pressure and gravity created oscillations in hot plasma. These left a permanent imprint in matter distribution. Today we can still detect that pattern, a fossil echo of ancient sound shaping the universe. Galaxies consume smaller ones. Over time, large galaxies absorb smaller companions. Their stars stretch into streams, then disappear into halos. The Milky Way bears these scars. Galactic cannibalism is slow, graceful, and inevitable. Some stars flicker like fireflies. Not all stars shine steadily. Some pulse, dim, and brighten in rhythm, driven by pressure waves, eruptions, or eclipsing companions. From Earth, they seem to flicker softly in the sky, blinking with a slow, steady rhythm. Some complete a full cycle in just hours, others take years. These changes aren't random at all. Many are incredibly precise, repeating again and again like natural clocks. Astronomers rely on them to measure distances across the universe. A single repeating pulse can reveal how far away a star truly is, and how bright it really burns. Stars don't just shine, some of them breathe. Some black holes drift through space completely alone. Not every black hole sits quietly at the center of a galaxy. Some are cast out. Gravitational encounters can eject a black hole from its birthplace, fling it away during a galactic collision, or kick it free after a violent merger. Once released, it becomes a rogue, moving silently through interstellar or even intergalactic space. These wanderers are difficult to find. They give off no light unless they disturb gas or tug at nearby stars, but they're likely out there, drifting unseen through the dark. No orbit, no companion, no home, just mass, motion, and the deep pull of gravity left behind by something that collapsed inward and never stopped falling. Even black holes can be kicked across a galaxy. When two black holes merge, they release a burst of gravitational waves. Those waves aren't always perfectly balanced. If more energy is sent in one direction, the newly formed black hole recoils like a cosmic kick, powerful enough to send it flying at thousands of kilometers per second. Some may be launched entirely out of their galaxies, doomed to wander between them forever. Others end up in wide, lonely orbits. Astronomers believe these kicked black holes exist, silent travelers pushed by the memory of their own collision. Even the most massive, seemingly immovable objects can be set adrift by the right kind of wave. Some stars are stripped down to bare cores of pure carbon. When a star like our Sun dies, it sheds its outer layers and leaves behind a dense core called a white dwarf. Many white dwarfs are made mostly of carbon, and under immense pressure that carbon can crystallize. In a very real sense, some stars become giant diamonds. These stellar gems are about the size of Earth but far heavier, glowing faintly with leftover heat. They no longer fuse atoms, yet they can shine quietly for billions of years before fading into darkness. Astronomers have even detected vibrations in some white dwarfs, a gentle ringing like a struck bell, a cooling jewel drifting through space. Once a star, now a crystal of ancient fire. Most of the universe's history is still ahead of us. 13.8 billion years sounds like a long time. But when you imagine the full future of the universe, not just tomorrow or a million years from now, but trillions of years ahead, we're still very close to the beginning. Stars are still forming. Galaxies are still taking shape. Black holes still glow with falling matter. One day the stars will fade, galaxies will drift apart, and the universe will grow quiet and cold. But that chapter hasn't started yet. Right now, we live in a bright season, a brief golden moment when the cosmos is full of motion, change, and light. The past is vast, but the future is larger still. Supernova remnants continue expanding for thousands of years. When a massive star dies, it explodes in a supernova, briefly shining brighter than an entire galaxy. But the story doesn't end with the flash. The shockwave keeps moving outward for centuries, even millennia, sweeping up gas and dust along the way. These expanding shells are called supernova remnants. They glow in radio waves, X-rays, and visible light, each pattern telling part of the explosion's story. Some form delicate filaments, others chaotic clouds. The Crab Nebula is one such remnant, still expanding from a blast seen on Earth in the year 1054. These remnants are the long, slow breaths of dead stars, continuing long after the light has faded. Light from a distant star can be twisted by a single planet. We usually think of gravity bending light on enormous scales by stars, galaxies, or black holes. But even a planet can do it. If a planet passes directly between Earth and a distant star, it can act as a tiny gravitational lens, briefly magnifying and warping the starlight. This effect is called microlensing. It's subtle and rare, but powerful enough to reveal planets we'd never otherwise detect, even in other galaxies. A small flicker, a gentle curve in brightness, and suddenly a hidden world announces itself. The planet may be dark and invisible, but the light it bends quietly says, "I'm here." The universe once glowed with a soft orange light. In its earliest days, the universe was a hot, dense plasma shining intensely. As it expanded and cooled, that glow changed. When temperatures dropped to around 3000 Kelvin, atoms formed, and light was finally free to travel. At that moment, the universe would have appeared orange, not the black sky we see now, but a warm glow filling everything. Over time, that light stretched into the faint microwave background we detect today. But long ago, all of space glowed softly, like embers fading into time. Some regions of the universe cool more slowly than others. As space expands, it cools gently, like a vast oven slowly turning off. But not every region cools the same way. Areas rich in matter or trapped radiation hold on to heat longer. Galaxy clusters, for example, contain gas that stays hot for billions of years. Other regions cool more quickly. These differences shape how stars form, how galaxies evolve, and how long certain processes last. The universe doesn't cool like a machine. It cools more like weather, uneven, textured, and quietly alive. One day we might witness the birth of a new universe. Some cosmological theories suggest new universes could form within our own, branching off through quantum fluctuations, black holes, or mechanisms we don't yet understand. If it happens, it would be far away, beyond anything we could reach. But in theory, signs might appear, a sudden expanding bubble of unfamiliar physics tearing itself free. We don't know if this has happened before. We don't know if it ever will. Still, the idea remains that even in darkness, something new could begin. A beginning inside an ending. A whisper inside silence. The universe is still ringing from its first moments. In the earliest fraction of a second after the Big Bang, the universe expanded violently in an event called inflation. That expansion left behind ripples, tiny fluctuations stretched across space. Those ripples became galaxies, stars, planets, and they also left echoes. We see them today in the cosmic microwave background, and perhaps one day we'll detect them as primordial gravitational waves. The universe may seem quiet now, but it still hums with the memory of its first vibration, like a bell long after it was struck. The universe is vast, and you are one way it knows itself. Of all the strange truths in astronomy, this may be the most quietly powerful. You are made of stardust. The carbon in your body, the calcium in your bones, the iron in your blood were all forged in stars. You are not separate from the cosmos. You are a moment of it, briefly aware. A small flicker of consciousness in a universe that otherwise only moves, burns, and cools. In that sense, the universe has grown eyes, and through them it looks back at itself. Thank you for spending this time here, drifting through the cosmos with me. We crossed vast distances, past dying stars and newborn galaxies, listened to echoes from the universe's earliest moments, and somewhere in all of that, there was you, breathing slowly, thoughts softening, maybe already asleep. This universe is full of motion and mystery, but also stillness. It holds light and gravity, but it holds peace too. and the fact that we can know it quietly, moment by moment, is something rare and beautiful. Wherever you are now, whether fully awake or drifting beyond thought, may your dreams be gentle, may your rest be calm, and may you carry, even faintly, the memory of a universe that glows not only above you, but within you. If you're still awake, you can continue with the next chapter. And if you'd like more stories like this, softly told and filled with wonder, you're always welcome to stay. Good night.